Okay, good morning everybody. Good morning everybody. So today my lecture is based on critical flow. In the last class, can anybody remember anything? It was related to specific energy, yeah. And we have already learned about specific energy and a specific energy diagram. So by using this specific energy diagram, we will learn some properties of critical flow today, right? So I have to write something here. So we know the equation of critical flow will be based on this equation. It is twice g and a squared. We know this is the equation for specific energy, right? So if I differentiate this equation with respect to y, that means if I vary the depth of water, what will happen with this specific energy? So that's why I have to differentiate this. This dE and dy is equal to, since I am differentiating this y, so it will be 1, we know the rules of differentiation, and I am just considering that the Q, the flow rate of the discharge, is constant, and G is always constant because it is acceleration due to gravity, right? So what will happen in A? Because we know if the area, right? If this is the channel bottom and this is the depth of water. So the area, inside area we have this variable, right? Depth of water. So that means A is variable here. So if I differentiate A, it will be this. And now, since it's differentiation, if I consider a very infinitesimal strip of channel and the depth is dy, the depth of dy is tends to 0, and this is B, or it is capital B. So what will be the area of this shaded section? It will be dA is equal to B dy, right? So dA divided by dy will be what? It will be B. So from this equation, if I simplify this, it will be q squared g aq, and it will be b. I'm just replacing this value here with b and simplifying this one. It is this. Still, on the left side we have this d and dy, right? And we also know the continuity equation q is equal to ab. And if I replace this q here, what I'll get? 1 minus, it will be b squared, a squared divided by g, aq, and b. So this is a squared, this is aq. What I will have here, it will be dE and dy is equal to 1 minus b squared divided by g, and b is here and a will be here, right? So I can just rearrange this way, b squared g and a divided by b, right? And we know the definition of hydraulic depth. In the previous lecture, we defined hydraulic depth is the ratio of cross-sectional area to the top width, right? For this case, it is b. Bottom width and top width for rectangular channel section is same. So I can replace this thing here, e square, g and d. And from the previous lecture, we also know the definition of Froude number. Froude number f is equal to, it is v divided by root over g and d. So I can write this equation this way, v divided by root over gd and square. So it is the same. So that I can replace this value with this Froude number. So still it is this one, right? So dE divided by dy is equal to 1 minus Froude number square. So after this differentiation, I am getting the change of specific energy with respect to depth, considering the flow rate is constant. I am getting 1 minus Fr squared, right? So see here from this curve if the specific energy is minimum. So when the minimum condition occurs in differentiation, if I just differentiate our equation or function, and if I take the first derivative, this is the first derivative as 0, then I will get this one, right? So 1 minus x squared is equal to 0, that means f is equal to 1. So that means f equal to 1 means it is critical. We know the Froude number is less than 1 when the flow is subcritical. When the Froude number is greater than 1, the flow is supercritical. And when it is 1, it is critical flow. So from this differentiation, it is proved that the flow will be in a critical state when the specific energy is minimum here. This is one property of critical flow. So what will happen if I just consider the E, specific energy is constant, and if the flow rate discharge changes? So I have to differentiate the same equation considering that Q is variable and E is constant. So by this way I can also prove that F is equal to 1. So that means at critical state of flow, the specific energy is minimum, however the flow rate is maximum. So what other property we can define from this equation for the critical flow, right? So by this time we know F is equal to 1 for critical flow. What is the equation of F? F is equal to V root over GV, right, is equal to 1. If I just square both sides, what will happen? V squared divided by GV is equal to 1. That means it is E squared is equal to GV, right? And I can just rearrange this equation. V squared, I'm just dividing by 2, and I'm taking G this side, so I have to divide this D divided by 2. Since I'm deriving this equation from the property of critical flow, so I'm just denoting C here for the critical. So this is another property. This is velocity head, we know from the previous lectures. So at the critical state of flow, the velocity head is 1/2 of hydraulic depth, right? So if I consider the channel is rectangular section, so what other property of critical flow we can derive, right? So you know the definition of specific energy, Y plus V squared over twice G, right? So if the flow is critical, then I can define this EC, it is YC, the velocity is VC. And we have just derived the velocity head is equal to what? 1/2 of hydraulic depth. And if the channel is rectangular here, right? So what will be the hydraulic depth? It is A divided by B. That means it is By divided by B is equal to Y. So for the critical section of channel, the hydraulic depth is equal to the depth of water, right? So I can replace this values here, YC plus, it is YC divided by 2, that means it is 3 by 2 or 1.5 YC. So this is the most important property of critical flow. If I know the flow is critical, so I can easily calculate the specific energy by knowing only the depth of water, right? So YC. So at critical state of flow, the specific energy is minimum, and the specific energy is 1.5 times of the critical depth, right? So there are some other property. The specific force is also minimum. So here, right? See, the specific energy is minimum for a given discharge. We have derived this here, and Froude number is equal to 1. We already know that. And discharge is also maximum. If I differentiate this equation again, I'll be seeing this same equation, which is F is equal to 1, which is the property of critical flow, and the specific force is also minimum, and the velocity head is equal to 1/2 of hydraulic depth. We have proved here, and we also proved for rectangular channel, the specific energy is 1.5 times of critical depth. So how can I compute the critical depth? So there are some equation here already. We derive this equation. If the channel section is triangular, we can directly use this equation. If it is wide channel or large river which has several kilometer width, we can use this equation. And if it is rectangular, for this section we can use this one. If I know the flow rate and if I know the width of the channel, I can easily calculate what will be the critical depth of water. Easily I can calculate this way. Or if it is triangular, we can use this one. If it is parabolic section, we can use that equation. Right? So this is how we can compute the critical flow. Right? So far, we have learned a very important topic in open channel flow, which is critical flow. But before learning this critical flow, we already learned about other flows, like uniform flow. But uniform flow is different than critical flow. So for computing any flow, or for designing any hydraulic structure, we need to know whether the flow is critical or not. Because from that graph, we can see at the minimum specific energy means when the flow is critical, we have only one depth. And if the specific energy is larger than critical specific energy, then there will be two depths. We have seen in the last class, right? So any depth which is lower than the critical depth, the flow will be supercritical. And any depth which is higher than or larger than the critical depth, the flow will be subcritical. So that's why it is necessary to know whether the flow is critical or not, or what will be the critical depth. So at first, for designing any canal or channel, we need to know the critical depth. And based on this critical depth, we can compute whether the flow is subcritical or supercritical. And based on this criteria, if the flow is subcritical, we need different computation or different types of protection or something like that. So this is how we can design or compute, right? So in the next class, or from the next class, we'll learn something about gradually varied flow. By this time, we already completed uniform flow, critical flow, all these things. So in real world situations, since the flow is not uniform, it is gradually varied. That's why we'll learn something about gradually varied flow in the next classes, right? So this is for today. So it is basically based on mathematics and differentiation. It is interesting to me. If you feel interesting, I feel it's interesting to you, so you can ask any question if you have any.
So if the channel is not an open channel, how can we calculate this critical?
This one? That is for pipe flow? Yeah, for pipe flow we have different hydraulics.
Okay.
Yeah. But the condition is same. At critical state of flow, the specific energy is minimum. We can plot the same diagram, right? For the pipe flow also. And we'll have one minimum specific energy for critical state of flow. But this is open channel flow, and we're assuming that the specific energy is measured from the bottom of the channel. That's why it is this. But for pipe flow, we may have this type of slope, or we may have this type of slope, right? For pipe, because sometimes we use the pipe for filling up our overhead tank. So then the direction of flow is different. That's why the hydraulics is different. We cannot assume that the flow is occurring from the bottom. It's different. We need a reference level.
All right, thank you.
Okay.